Uh, all right, everyone. Welcome back to this channel. Uh, Thanks for coming. If you did. Uh, so again, we are back with the series of making AI morally conscious. We are back with that series. Um, and in this video, we are going to go through this paper, optimal tendencies, 10 to seek power. We try to derive. I think that there is some derivation, some mathematical derivation. We'll go through that. Actually, I use ChatGPT to summarize it so that we don't have to like read everything. Uh, and actually, I think ChatGPT makes it much more clear for us. Actually, elaborates a bit, which is quite interesting. Uh, so we'll go through. So we'll go through this part. So definition 3.1. Sorry, rewardless MDP. So let's see what that is. So uh, SAT. Let's see what. So I think S is. So yeah. So S is the state, the finite state. I think with finite actions. That's what finite state means. And then we'll have A, which is action spaces, I think actions, and then uh, transition function, which takes in, yeah, so which takes in S and performs the action A to get the changed S, the changed state. That's what we'll get. The delta S, the change in S after performing action A. So we'll treat the discount rate. So actually, I'll tell you what discount rate is. In reinforcement learning, the discount rate. The discount rate is a metric. Right? It's a number between 0 and 1. So it's a number, right? And then so the if the number is closer to 0, then that means the future prop. Then that means that you know immediate rewards would be will only be calculated. So the model with the reinforcement model, the RL model would basically be myopic. Myopic means it can only see like nearer possibility of reward. So it only calculate nearer outputs. But if the discount rate is higher or closer to 1, then more long-term predictions or long-term you know rewards would be considered. Long-term rewards should be considered. That is what uh, the discount rate is. It's a metric that defines whether uh whether we should whether we want the model to uh, consider short-term rewards or long-term planning or long-term rewards. That is what it means. uh right, with domain 0 and 1, between 0 and 1, I think. And with different 3.2, we have one cycle states. So let's see what that means. So this is a rewardless MDP, which is, I don't know what that means. I think finite is the keyword. Uh, let's see what this is. Reward one cycle states. Let ES will be a real number. So ES, what is E? I don't know. Be the standard basic vector for state S. So that is a standard basic vector, I think. So that there is a 1 in the entry of state S and 0 elsewhere. Okay, state S is a 1 cycle if I don't know. I don't know about the notation. So let's see how ChatGPT defines it. Uh, that is rewardless MDP. Okay, it's okay function. I will state it. Okay, okay, very interesting. So let's say what 1 cycle state is. We could ask it to even like elaborate it, which is quite interesting. It's 3.2. Yeah, 3.2 1 cycle states. Uh, status is a 1 cycle if there exists an action A such that T of S comma A is equal to S, where ES is the standard basis vector for status. What minute? Sorry for that. Sorry for that disturbance. If we heard it. Yeah, I'll get back to that. I should probably hide this, right? I'll hide this. I'll hide the floating meeting controls on that. Uh, so this is where we are, right? So where S is the standard basic vector for state S, a vector with a 1 in entry of state S and 0 elsewhere. A status is terminal state. Okay. Okay. So a status is a terminal state for all actions. Terminal state. What is a terminal state? I think let's go. Let's see. I think we could use this. I'll just let's just let's just write it. What is that? Terminal state. Let's send that. Let's see what that is. Is a state which no further okay transition possible regardless of that. That means uh the end stage, right? I don't know if this notation is even relevant for RLHF. I don't know. Maybe it is not. Maybe is it? What is action space, right? So the state is uh the reward function. So no, right? The state. Okay, so we have an environment. Let's say we don't have to like define every detail. Let's say action is taken. Action is updating the fine tuning the model, and then we have the reward function. Okay, we do, and then it's like a game. It's a never ending game actually, right? There's no necessary terminal state, or maybe because it has a terminal state, it's got like one cycle, maybe. Uh, the T of S A equal S, where A is a standard basis of our state S. So we have a state S, uh, which is the terminal state for all actions. So what is this symbol? What is that? And I've never seen it before actually. I think it is like uh denoting that it is a real number or something, or belongs to. Okay. Okay, so it belongs to that distribution. I think that is what that is. So A belongs to A comma T of SA equals A. Yes, so okay, that does make sense. Okay, this actually small a belongs to A, and T the transition function of S and A is equal to ES, which is I mean any possible basis vector for status, like all the possible variations. Uh, okay, that's called a one cycle state. Maybe we could some elaborate on one cycle state. We could ask that. Elaborate on one cycle state. Mhm. Let's try to read this. I don't care if it takes a lot of time. I think uh, we could do it. I mean, again, we are not progressing that fast. Really, I mean, I'm a bit concerned. Maybe we are falling back. Maybe we are not necessarily doing the work required. Right? Mm, one cycle state in Markov Desert process is the state that has deterministic transition back to itself when a specific action is taken. Okay. Okay, that does make sense. So there is no change in this position. That what that means. This concept is important, right? So okay, this concept is important to understand the agent's behavior and structure of the MDP. Okay, definition: status is a one cycle if there exists an action A, uh, that belongs to the vector A, such that the transition function SA returns S with a certainty. What is certainty? In other terms, using a standard basic vector which has one in the entry corresponding to S0. So it can be expressed as interesting. Uh, Consider simple MDP with three states. S is equal to S1, S2, S3, and a set of actions. Let's say A1 and A2. Okay. So state S1 is a one cycle state. Uh, as one cycle state. Let's say if the agent is in one state one S1 and take action A1, it will always remain in S1. Formally, T of S1 equal to A1, where ES7 is equal to 1 comma 0 0. Well, that because the first action, the first set, I think, yeah, the same set is returned. Uh, sorry, the set the same state is returned. Uh, and that means that if the agent is in S1 and chooses action A1, the next state will be S1 with probability S1. Okay. That does make sense. We don't have to like do it again. Very like model is very powerful. I think I'm using ChatGPT 4.0, uh, and man, it's like powerful, right? Like really smart. I'll tell you that. I mean, of course, I will definitely recommend you to use it. Okay, one cycle state finished. That's what one cycle. That's a definition. The mere definition for to continue in this paper. Okay. Um, State visit distribution. Let's see what that is. 3.3 state with distribution. Given what is this? Some variable is equal to AS, the set of stationary deterministic policies. The visit distribution induced by the following. I can see everything, so I'll just make this so you're smaller, right? The set of state the visit distribution induced by following policy pi from status at discount rate 0 or 1. Okay, that means uh okay, that belongs to 0 and 1. That could be anything, right? That is what that means. Is f of pi of f of pi comma s is equal to. So let's see what that f means. I think we do have it. We do have it in this paper. Let's see what that means. Okay, that is going to change into f. The f is going to change uh, into the sum of t to from 0 to infinity. T is the I think terminal function. No, the notation is all over the place. I don't know what we have. Okay, y. Okay, y of t. So yeah, t is a variable. Sorry, I'm sorry. That is a variable that just loops in. So we have discount rate that will have t multiplied by uh, e of st, that belongs to uh, pi from policy pi. Okay, we have st, this current state. So we'll have to like add up all. Okay, so we have. So I mean, we of course I don't think we have like infinite uh, t's. Let's say infinite discount states. So we have all this. So we're just going to like okay, that is very interesting. Let me just elaborate on elaborate the definition 3.3. Elaborate definition 3.3. Mhm. Hmm. Right. State visit distribution. Okay, that is a lot of that surely is a lot of elaboration. Okay, example for clarity. Man, the model is powerful. Like really powerful. So right. Definition 3.3 state visit distribution. Given a set of stationary deterministic policies, the visit distribution induced by following policy pi from state as discount rate is the visit distribution. What is the visit distribution? Oh man, I'm really bad at notation. That is sure. Yeah. In context of refers to the probability distribution over states. Probability distribution says that an agent visits when following a particular policies from a given start state. Okay, interesting. Uh, Probability distribution over states that an agent visits when following a particular policy from a given state. From a given start state, a particular policy is followed, which is a consistent policy. I think it's consistently followed. Wait a minute. Right, it is consistently followed. So, mm, okay, from a given start state, the probable distribution of the distribution accounts for the likelihood of the agent being in each state over an infinite time horizon discounted by a factor. Okay, okay, so we have a distribution that contains the likelihood of the agent being in a specific state, right? So there could be many states, and so that is what that means. The visit distribution and discounted by a factor. So we also have factor. So let's go through this. I think, right? So okay, so we have this distribution that is going to change based on the sum of yt multiplied by e of st. Okay, here f by s is a visit distribution function, and f is a set of all such functions. Okay, interesting. So we have many functions. Okay, uh, with many policies, right? We have many policies that are. So let's say this is the total number of policies, uh, and then for each policy we are going to have a specific, uh, you know, uh, what called visit distribution function, in which we are going to have the probability of each state being achieved or each state being reached. So we have that. Again, we also have the discount function by accounting for how few how how that that controls if you want to prioritize immediate rewards over future, uh, let's say, profit. And we have, it's okay, breakdown of the definition. So set of stationary deterministical policies. Okay, I like, okay, I mean it does make sense, right? I don't think we need further. I don't think we need further explanation. Uh, or maybe we do need a further like. I mean, the model is very good, right? This is the only thing. All my attention is going to this thing. The model, how powerful, how great, how wonderful this model is. It's wonderful. It's very useful, right? Yeah. Okay, anyway, break down the definition. Set of standard deterministic policies. Uh, let's say large pi is defined as A as representing all possible matchings from state S to action A. Each pi, belongs to big pi is a stationary deterministic policy, meaning it deterministically prescribes an action for every state and does not change over time. Okay. Okay. Uh, so visit distribution function. The function describes the probable distribution over state that an agent will visit when following policy pi, starting from state S, taking into account the discount factor uh, gamma. Okay. So discount factor gamma, the discount factor, okay. We know that. Explanation explain expected states represent the expected value of the standard basic vector of the state S t at given time. Given that the agent starts from S and follows policy pi, the expectation is taken over the states visited according to the policy pi. Interesting, right? It's simple, right? Summarize over time. We'll just add uh, all the, or let's say all the states, right? We'll just add all the states. Let's say Yeah, we'll just add like through all the states, all the possible states. And then example for clarity, okay, that we don't need that. Um, yeah, that's like example importance, right? This may be a little important. So the state visit distribution function is crucial in analyzing and understanding the behavior and long-term visitation patterns of an agent under a given policy. The range of states an agent can potentially visit and how often weighted by discount factor, evaluation comparison of different policies based on induced state visit distribution. That does make sense. Uh, so what is this? We are okay. Definition 3.3, right? So let's see what we have here above over here. Um, right, so we have definition 3.3. Okay, single state restriction. Like, is that it? Is there anything else between 3.3 and 3.4? First we sometimes okay. Actually, definition 3.5. I think we can get to like this definition. There's no necessary conclusion, but you know, let's get to definition 3.4. Let's see what that is. Single state restriction. What is single state restriction? Maybe we'll know as we go on. 3.4 F single state restriction. Considering only visit distribution function induced by policies taking a state. Only visit distribution function that induced by policies taking a at state 0, S0. F of S given pi of S A equal S. Okay, so only this action is taken over this. Okay, for at this state, that is going to be equal to okay, what is that? F that belongs to F of S given. I mean, yeah, we certainly do need an explanation. That notation is very hard to understand. It doesn't really make sense, right? We'll just ask it to elaborate definition 3.4. The single set restriction of the set of distribution functions FFS focuses on the visit distribution functions induced by policies that take a specific action at a given state. This concept helps in understanding the effects of specific actions in a particular state on the overall behavior of the agent. Okay, this concept, okay, uh, focus on visit distribution induced by policies that take a specific action at a given state. This helps you understand the effects of specific action in a particular state on the overall behavior. Okay, formal definition, considering only visit distribution functions into this policy as okay, that's breakdown of definition, state SO and action A. The restriction focuses on the behavior of a agent when it takes a specific action A at a specific state SO. Okay, policy pi, okay, that takes an action. Visit distribution function induced by policies. Okay, restricted set. This is a set of visit distribution on function F that can be achieved by following some policies pi that specifically takes action A at okay. So we only get that specific, I mean, visit distribution function. Okay. Okay. So considering MTP with states and action A, suppose a transition are defined as from S1 A1, from S1 A1 leads to S2 and A2 leads to S3. From S2 A1 leads back to S1 and A2, okay. From S3 both A1 and A2 lead to S1. So we have a specific, let's say, a path. Let's say there's an S1. So maybe we could like draw diagrams here, but that's not necessary. Imagine we are interested in the distributed function at from S1 when the agent takes A1. Okay, identify all policies. Pi says that pi of S2 equal A1. Okay. So we identify all the policies. Okay. Uh, okay. Compute visit distribution from pi for pi 1 and pi 2. And then we'll get this restricted set from this visit distribution. This is useful for analyzing how specific action itself influence the agent's behavior. And this resulting distribution for visit it allows for focused examination. So we'll add, so yeah, again, this for more focused examination where a specific action is took at is is taken at a specific state, right? And then we'll get like all the policies that do fall the do let's say that do select that specific act that specific state, and then we're going to find the visit distribution for these policies. uh okay, very okay, that is what that is. Okay. Okay, that very interesting. So we have definition 3.5, which is a value function. Let's get to definition 3.5. What that is. This is the definition 3.5 for a policies for a policy pi belonging to the big pi and any reward function r over the state space. The on policy value at state s and discount rate y belongs to sorry discount rate gamma that belongs to 0 1 is distribution. So is v. What is v? Do we have any v's? No, we don't. So maybe that doesn't really, yeah, maybe that's a new function. So vr of s and y, vr of pi of s and gamma, that is changed by the rigid distribution of y transpose r. Is that transpose? Yeah, that is probably transpose of gas. Sorry, gamma r, where r belongs to real number of s states. Is r expressed as a column vector? Okay. The optimal value is the max. Okay, so we'll have to like, so yeah, let's see let's elaborate. Right, let's say elaborate definition 3.5. The value function in the context of, okay, let's the value function in the context of Markov decimal process, the measure of the expected cumulative reward that an agent can obtain from a given state when following a particular policy. Okay, so it's again it's a measure. It's a measure. So we have to like, these are all definitions that are laid out to measure things. So it helps to quantify how valuable it is for an agent to be in a specific state, considering the rewards it can accumulate over time. Uh, Formal definition for any policy pi, the reward function r and the discount rate gamma belongs to 0 and 1. The value function v is defined as follows. Because we have this value function. Okay, so the value function, right? Okay, so v by value function p by policy that reward the specific reward and given state s and a gamma function, right? So we have this which is going to be the visit distribution of pi s. uh, so yeah, what is the visit distribution doing? So we are taking that specific policy, we are going to uh, right. So what is let's get back to the equation. Let's try to analyze everything. I'll try to analyze everything. Right. So we are taking the gamma, multiplying that by the uh let's say probability of each state. So or we are multiplying that by uh so is a expected value when that agent is following by expected value. So we have multiple states. And okay, yeah, it does make sense, right? So we have each state, and then we are going to, so for each state we are going to multiply the uh I mean, is it related to like the probability? That is it probability? Is this a probability? I'll see. Sorry. The context of visit distribution function. Okay. Expect the return expected value of the. Okay, so corresponds to the probabilities of being in each state t at time t under policy pi. Okay, that does make sense. So of being in each state st. Okay, so that is a probability of being at a state. So that is what. Oh shit. we we reached that limit. Shit. We will not be able to like use this amazing model. Absolutely awesome. It's awesome model. We will not be able to use it. We'll use it. We'll use a normal one. I'm not rich yet to buy to buy the rich shit. Right. So we have so what we are trying to do is to the value function is basically the visit distribution function of policy pi and s. So how often we will visit a function. And then, okay, so this is a visit division function induced by policy pi from status as defined in this Simple 3. R is a reward vector. Okay, we have R here, which is a reward vector where each entry RFS represents the reward for being status. Okay, that is very simple, easy to understand. So we'll take each state, we'll take each action, we'll take the probabilities, we'll add them in the visit distribution function, and we'll multiply them. Multiply each yeah, we'll multiply value with the reward vector to see how how valuable or how much reward we are getting. And then we have the dot product giving the expected outcome. Okay. uh, and then dot and value function is the max, so we are trying to improve this as much as possible. That is the optimal value function, right? Just like gradient descent, or yeah, something like gradient descent. So we are trying to like improve here, maximize. And yeah, that does make sense. That is a visit. So that is a value function where we are going to use for metric. Sorry for that. I'll hide with floating mid controls. uh and then let's see what we have next. So we have definition 3.5. We finished definition 3.5, the value function. And then yeah, we have got a lot very fun. The value function finished, like non-domination. A visit distribution function is non-dominated, that belongs to f of s, is non-dominated if f of nd, okay, what is that notation? uh it belongs to f of pi, uh that belongs to f of s. So we'll take f of pi. Okay, that is, yeah, we definitely do need. So is non-dominated if there exists some reward function r and discounted gamma such that f of pi achieves a higher value than any other f of pi in f of s. So we'll try to, you know what, I think we will end this video here, because I think we have done a pretty good job of understanding a lot of things, right? So I mean, uh, good job. So let's again for this the freakishly confusing notation. We'll come back to this tomorrow. I'll try to find a better way. I mean, again, ChatGPT 4.0 is very awesome. This is amazing. I mean, I'll highly recommend you to use it in your own journey. Uh, let's try to see what this paper. Let's try to see what this paper comes to. Maybe this is a total like waste of time. Maybe this is not very relevant. But again, we'll try to go through this paper, right? We'll try to go through this, and maybe with the next two videos, we could hopefully finish this paper. Uh, So yeah, and maybe the next two videos will be quite large because I'll record them in the morning and I'll upload them. So again, for this for now, thank you for watching, and I will see you in the next video.